Hello, my name is Mackenzie Stephanie.
Hello, my name is Byron Henderson, and tonight we'll be explaining to you all our first thermodynamic project. So, the problem statement states that a power plant is driven by a gas working fluid and designed to deliver a net output of 100 kilowatts. The power plant features three reversible processes, such as a heater, expander, and cooler, with nitrogen as its working fluid. In accordance with our project guidelines, this project illustrated a gas power cycle consisting of the following three different processes: a constant volume process going from T1 to T2, which means that it was an isochoric process because isochoric means that the volume will remain the same. And anytime I refer to something with a number after it, such as T1 or P1, that just means that that's the temperature or pressure at the state in our process. So T1 refers to state one, T2 refers to state two, and T3 refers to state three. Um, Continuing on and going on, P1, an adiabatic expansion that results in a suggested percentage increase in the specific volume of the gas to P1 and gas compression.
So, I will be discussing the project goals. To perform this gas power cycle, we will have to determine the unknowns at the different states, which are the temperature, volume, and pressure. Next, we will then move on to finding the necessary compositions that will help us solve the gas required in the thermal efficiency. And then finally, nitrogen will be evaluated throughout a PV, which is a pressure volume diagram.
Anytime we solve a problem in thermodynamics, we have a three-step process. So the first process is to identify. Next is formulate, and lastly is solve. So whenever we identify something, we have to sketch it out first to see that so we can get a visual of what we're trying to solve for, and then we state all of our givens given to us. And in this situation, our diagram of sketching it out is referred to as figure one. And so that was a schematic cycle that we made. And in the schematic cycle, we listed all the givens that were given to us in the problem statement. And then we had question marks for everything that they wanted us to solve for, but we didn't have for at that time. And we were also given the volume expansion going from state two to state three, along with other things as well.
So, next, we'll be moving on to the second step, which was be the formulate. We have to formulate concepts, key equations, and the assumptions. This power cycle utilized five major formulas. The first formula was the ideal gas law, and we use that to solve for the ideal gas unknowns, which I previously mentioned, which was the temperature, pressure, and the volume. And that equation was PV equals RT, and we use that for state one and state two. The next equation was an interpolation, and we use that to solve for the enthalpies at different temperatures, and that equation was y1 plus x minus x1 times the change of y over the change of x. The next equation that we used was the adiabatic formula that was given to us from our thermodynamics textbook 3.18. And that was used to calculate the temperature for state three. And that equation was T3 over T2 equals P3 over P2 to the power of R divided by CP. The next equation was the mass flow rate. That equation was used to calculate the specific heat added or rejected, which was our Q. And to calculate that, we did m dot equals W net over change of H. To solve for Q, we did m dot times the change of H. The last equation was the thermal efficiency, and that equation is basically the ratio of work done by the heat supplied. The conversions used are summarized below. You're able to see that we had to convert from Fahrenheit to Kelvin, and that's because in the ideal gas law, all temperatures will have to be in Kelvin. And since ours was given to us in Fahrenheit, we had to convert that. Also, our pressure was given to us in PSIA, and we had to convert that to pascals because that's the unit you have to use in the ideal gas law. The next conversion was kg per second to pounds per hour, and that was a mass flow rate unit that we were required to give the answer in. The next equation was kW to HP, which was the unit required for specific compression work. And then we had to convert kW to BTU, which was the unit required for specific heat added slash rejected.
In the last step of the process is to solve. And as Mackenzie stated, the two main objectives that the problem wanted us to solve for was the thermal efficiency and the amount of gas required to power the power plant. In order to find these two values, we had to do a lot of other equations in order for us to get the values needed for us to actually solve for the thermal efficiency and the amount of gas required for us to solve this system. And as you can see, we made the assumptions that V1 is equal to V2, due to it being an isochoric process at state 1, and P1 is equal to P3 due to it being an isobaric process at state 3. And the key compositions are shown in table 1. So as you can see, we have phase 1, 2, and 3, and these were all of our temperatures, volumes, and pressures that we found at each of those states, along with our enthalpy as well. Figure 2 is our PV diagram, or also known as our pressure volume diagram. So each pressure and volume that we found at the different states, we just plotted them on this graph, or this table, excuse me. And table 2 shows our the heat capacity that we use in order for us to solve for different things throughout our process. And heat capacity is also represented as CP. And table 3 exhibits the values that we use to interpolate for enthalpy, because the values that the temperatures given to us aren't on this table. And since they weren't on this table, we had to use a formula that Mackenzie was referring to earlier in order for us to find the correct enthalpy for that value at that specific temperature.
I will then move on to discussion of results. The implementation of formulas, assumptions, and the ability to solve different phases were the essential factors of solving this power cycle, which you were able to see from Byron. The compressibility factor of nitrogen was also close to 1 in the first two steps. The first one was 0.998 and the second was 0.99, which means that our gas was at its ideal gas state, and then it changed drastically when it entered to state 3.
Okay, so to summarize, the information used for specific heat enthalpy to solve for the equations that we needed were obtained from tables 2 and 3, as we mentioned earlier. And as Mackenzie just stated, nitrogen did not remain an ideal gas throughout the entirety of our process, because in states 1 and 2, it was like 0.01 and 0.02 off of it being 1, which is an ideal gas state. And in state 3, it was drastically different. So that's why we couldn't use the ideal gas law when we were solving for state 3, because it wouldn't apply anymore, because nitrogen wasn't an ideal gas anymore at that specific point in time. And the results from our power cycle could have been different if we used formulas to solve for things such as heat capacity and specific heat, but we use tables. We use tables that have predetermined values to help us this time. Maybe in the future we'll solve for those instead of using the predetermined values to dictate what number we use in order to solve for these formulas.
So you're able to see our references of there where we got most of our formulas and most of our notes. We just want to say thank you for tuning in and watching this video all the way to the end. And we hope you enjoyed our gas power cycle.